Okay, let's talk about something that, let's be honest, gives a lot of people a major headache on tests. Time, speed, and distance problems. You know the ones. But what if I told you there's a way to crack the code? Let's dive in. Right? You see a problem about two trains leaving opposite ends of a station, and your brain just shuts down. It feels like they're designed to be confusing. But I promise you're not alone, and there's a way simpler way to think about them. And this is the whole secret right here. Seriously. Forget trying to memorize a dozen different formulas for every situation. Every single one of these problems, no matter how complicated it looks, fits into one of two categories. That's it. Just two.
So, let's break this down. The game isn't about memorization, it's about identification. Once you can spot which of the two types you're looking at, you'll know exactly which tool to pull out of your toolkit to solve it.
And here they are. On one hand, you've got one body motion. Think of this as one object's journey, just told in different chapters. Like biking to the store and then taking the bus home. On the other hand, you have two body motion. This is all about two different things moving at the same time, relative to each other.
So let's start with one body motion. These are probably the most common type you'll see, and lucky for us, there's a really clean, structured way to solve them every single time. It's really just a 4-step process. First, just visualize what's happening to make it feel real. Step 2, you organize everything you know into a simple little table. Now, step 3 is the secret sauce. You find the one piece of information that doesn't change in the problem. And finally, you use that constant to build your equation.
Okay, let's make this real with a classic example. Jane bikes to a shop and then takes the bus back home. And the problem says it's on the same route. Ding, ding, ding. That's our keyword. It's practically screaming at us that the distance is the constant here.
And this is where that DST table becomes your best friend. Look how clean this is. We just plug in what we know. The speeds are 5 and 20. We don't know the distance, so we'll just call it X for both parts of the trip. And since time equals distance divided by speed, well, that last column just fills itself in.
Now for that last little piece of the puzzle. The problem tells us her total trip took 1 hour. So we just look at our neat little table, add the two time expressions together, and set the whole thing equal to 1. And just like that, we've built our equation. No sweat.
You solve that simple equation for X, and there's our answer. The distance one way was 4 miles. See? By organizing the information first, the actual math at the end becomes super straightforward. Now, there is another really cool way to tackle some of these one-body problems, and that's by using average speed. But be careful. It's not what you think. You don't just add the speeds and divide by 2. The only universal formula that always works is total distance divided by total time. But while that universal formula is your safety net, there's this fantastic little shortcut you can use specifically when the distance is constant, just like in Jane's round trip. It's 2 times speed A times speed B, all of that divided by the sum of speed A and B. Now just watch how fast this is. We plug in Jane's two speeds, 5 and 20, and bam! We find her average speed for the whole trip was 8 miles per hour. And since she traveled for exactly 1 hour, her total distance must be 8 miles. So, the one-way trip? Gotta be 4 miles. We got the exact same answer, just by taking a different path. All right, you ready to level up? Let's shift gears to our second category, two-body motion. This is where you get those infamous problems with two trains coming at each other, and it has its own really cool trick. The master key for unlocking all two-body problems is this concept called relative speed. Basically, instead of trying to track two different moving objects in your head, we just combine their speeds to turn it into a much simpler problem with a single interaction. And the rules for this are so simple, it's beautiful. If two things are moving towards each other, you just add their speeds to get the relative speed. If they're moving in the same direction, like one car trying to catch another, you subtract the slower speed from the faster one. That's it. So let's put it to the test. Here we go. Two trains, a 100-mile track, starting at opposite ends and just barreling towards each other. This is a classic two-body problem if I've ever seen one. Let's walk through it. First, we figure out each train's individual speed. Okay, since they're moving towards each other, what do? We add their speeds. That gives us their combined or relative speed. Now we can basically pretend they're one object closing that 100-mile gap. So we divide the distance by that relative speed to find out when they meet. From there, it's easy to see how far just train X traveled in that time. And what do we get? Train X traveled 37.5 miles before they met. You see? By using relative speed, we took what seemed like a really complicated scenario with two moving parts and just boiled it down into one simple calculation.
Okay, so let's zoom back out for a second and put all of this together into a really clear, simple framework you can use for any time, speed, and distance problem that gets thrown your way. It really comes down to this. The very first question you have to ask yourself is, am I looking at one object or two? If it's one object on a journey with multiple parts, your go-to tool is that DST table. It'll organize everything for you. If it's two objects moving around, your go-to tool is relative speed. Identify the type, then apply the right tool. So by breaking it all down into this simple framework, you've basically turned these anxiety-inducing problems into puzzles that you actually have the keys to solve. So the only question left is, which one are you going to tackle first?